Okay, I'm going to do an example. Cargo plane A and cargo plane B start from rest. Okay, so zero velocity initially. Assume both airplanes have the same engine, so they have the same thrusting force and negligible friction force. Basically, they're just telling us to ignore friction, and there's the same force from their engines pushing them forward. So if you want to annotate some things, they start from rest, same thrusting force, and we don't need to worry about friction. They both accelerate over the same distance of runway before they get in the air, so they haven't taken off yet. Cargo plane A is going twice the speed of cargo plane B before take out. Oops, this should be take off. So really these could just be cars, you know, starting from rest, going faster and faster down the runway. So let's work through this. We're going to start with our initial L and work our way through it. The exact order that you do this, here we go, let's see if we can zoom in a little bit there, could be different. I'm going to start with, I know they're on the runway the whole time. I know we're talking about airplanes, but we're not taking off. So I'm going to start with, given that they're on the ground the same time. So given that they are on the ground the entire time. This is a little shortcut here. So given that they're on the ground the entire time, this means, so here's my evidence. This means, well, the UG is 0. UG is 0 for both at initial and final. At initial and final. So I'm not just doing the initial, I'm doing both here, but because it's on the ground the whole time, it's just kind of a low-hanging fruit. It's an easy one to sort of start with. That's a 0. Okay. Now I need to do, so I did my initial UG, I did my final UG. So, oops, I forgot energy transfer. That should be in this little helper thing. So I got to do my initial K. Okay, so if I reread the problem, oh, they start from rest, okay? Given both start from rest, well, this means 0K for both. 0 kinetic energy, or K energy initially for both. Okay. All right, well, this is shaping up to be no energy to start with. So where do they get some energy? Well, they get some energy from an outside force. This thrusting force from the engine is adding some energy. And let's see, we know the same thrusting force over the same distance. Oh, one thing to note here is you may say, oh, you didn't talk about mass here at all. Normally, you would say, hey, you got to talk about mass. But if we look at these equations, my velocity is 0 at the beginning, so it doesn't matter the mass. My height is 0 at the beginning and at the end, so it doesn't matter the mass. So if my velocity or my height is 0, you don't have to address mass. And that's good because we don't actually know what the mass is here. That's the question we're trying to answer. So we need to do energy transfer. So for energy transfer, we're looking at this equation here. The thrusting force from the engines times the distance over which that force was exerted. So I got to compare those. And it actually says same thrusting force, negligible friction, which means I can ignore friction, and the same distance. So that's kind of an easy one. So given same thrusting force Thrust is like kind of the force that comes from like a rocket engine or the big turbine that are on the plane engines. Given the same thrusting force, exerted means like acted or applied over the same distance. Okay, so same and same. Hopefully I don't run out of room here. This means both planes gain the same amount of energy or have the same amount of energy added. Have the same amount of energy added. Okay. So we go back up to the LOL. So we need to show energy going in. So I need an arrow pointing in to here. So I could do it like this, or you should only do one of these. Hopefully you're listening and not just copying down what's on the screen. You could do it from this way here. You could do it from this way here. It doesn't matter as long as you have energy going in. So I'm gonna kind of get rid of those. So we need to figure out how much energy. Let's just say, I don't know, 4 blocks of energy. I just kind of made that up, so it's +4. Same thrusting force over same distance. Again, we'll do +4 here. 1, 2, 3, 4. So now I do my equations. 0 plus 0 plus 4 equals something plus 0. Oh, it's got to be 4. So plane A ends with 4 units of kinetic energy. Plane B ends with 0 plus 0, 4 units of kinetic energy. Now be careful. The question is asking about the greater mass. Mass is nowhere in this LOL diagram. So even though the LOLs are exactly the same, that does not mean one has a greater mass. So we got to go back to our given information, and there's got to be some other information about this final energy. Remember, kinetic energy is calculated by taking 1/2 the mass times the velocity squared. We already know twice the speed, or we want to find the mass. We know this, so we must be given something about the speed, and that's this. So if plane A has twice the speed, but the same kinetic energy, in order to balance this equation out, in order to have the same sides, balance out, equal the same thing, I gotta have less mass. And that's what we're gonna write here at the end. Both have amounts of, so we gotta do our conservation of energy and then put it all together. Since energy must be conserved, so we can't just disappear energy. Energy can be added. We just have to know where it's coming from and account for it. Since energy must be conserved, this means they both end with the same final energy, which is all K. Which is all K. So same final K. All right. So I've talked through my entire LOL, every single bit of it, and now it's time to answer the question. Make our connection, I call this the concluding statement. So it says, and I'm going to write it down here because I ran out of room. I can't just say, oh, airplane B has more mass and be done, because I got to connect it to this. So same final K, and we can talk about A or B here, but I'll talk about A. Same final K, but A has more speed means A must have less mass. And normally I would write this up here, but I ran out of room, and that's fine. Oh, sorry, Liz. Okay, so now and my concluding statement, I'm always going to look at one of the energies, and I'm going to know the comparison between the energy. I'm going to be given one of the other values, and then I'm finding the last one. All right, I'm going to briefly kind of go over this as like a big picture here, just kind of a summary. First, we did the initial L, or we did the UG, right, for the initial and the final. We took a shortcut. You don't have to do that. And then I did my initial L. I finished that off. So given that they are both on the ground the entire time, this means UG for 0 for both. UG is 0 for both at initial and final. Given they both start from rest, this means 0 kinetic energy initially for both. Then I got to do my energy transfer. We do have an outside force, in this case, adding energy to the system, making it go faster and faster. Given the same thrusting force, exerted over the same distance. So what I'm thinking about here is the amount of energy transferred is equal to the force times the distance that force is exerted. So same force, same distance, same energy transferred. Both planes have the same amount of energy added. Everything's the same. Since energy must be conserved, we're figuring out our final missing energy in our LOL, which is the final K. Since energy must be conserved, this means they both end with the same final energy, which is all K, so same final K. Now, that doesn't connect to mass. You have to connect it back to mass with a concluding statement. So in this case, mass is in both equations, but we have 0 UG for everything, so that doesn't really help us. So here, again, same final K, but A has more speed, so A must have less mass, okay, to get the same, to balance that out. All right, hopefully that was helpful.